Have you ever heard this pulsating effect when tuning an instrument? Do you hear how the sound of the two strings seem to interfere with one another? In this video, you'll learn why we hear these beats and the beautifully simple math behind them. Let's start with a more controlled demonstration with two sine tone generators. This smartphone will play a 440 Hz tone, which is the musical note A. Meanwhile, this tablet will play a slightly detuned 441 Hz tone. They sound almost identical when played separately, but of course the 441 Hz tone is slightly higher pitched. But listen to the beat that arises when I play the two tones together. As you can hear, when these two tones are played together, they interfere with each other acoustically and create a pattern of pulses. In acoustics, this is called a beat. If you know why this is happening, leave a comment below with the answer. If you don't know yet, that's okay. Stick around because I'm about to explain it. First, let's experiment with changing the frequency of the detuned tone. Instead of 441 Hz, let's do 442 Hz. We still hear a beat caused by the interference between these two frequencies, but this time the beat is faster. Here's 441 Hz. And here's 442 Hz. I've set up a session in the DAW so we can visualize how these two tones interact. The 440 Hz waveform and 441 Hz waveform line up pretty well in the beginning. The positive sections align and the negative sections align. And this means the two waves will sum together to create a stronger wave. But as we scroll forward in time, the waveforms start to get more and more out of phase. You can see that on the top track. Eventually, we reach a point where they're completely out of phase with one another, where the positive section of one aligns with the negative section of another. At this point, the two waves will work against one another, which results in cancellation, where the combined result is almost total silence. As we scroll further, this pattern repeats itself. In phase, out of phase, in phase, out of phase. I've mapped out these points with markers along the timeline. As you can see, they follow a very consistent cadence. In this case, every half second, the waves will either be fully aligned and in phase, or fully misaligned and out of phase. Stated in hertz, or cycles per second, the beat that occurs when we combine 440 Hz and 441 Hz is 1 Hertz. Let's listen. Now let's change the frequencies to see how the beat frequency changes. Now I've marked the beat created between 440 Hz and 442 Hz, and you'll notice that they occur twice as frequently. Now the beat occurs twice per second. And this pattern continues. The difference in hertz between the two tones equals the frequency of the beat. Listen to how the number of beats per second corresponds to the frequency offset between the two tones. We'll start with 440 Hz to 441 Hz. 442 Hz. 443 Hz. If you're tuning an instrument like a guitar and you don't have a tuner, this can be a helpful tip. You can excite the same note on two strings. If you hear a beat between the frequencies, that's an indication that those notes are close, but not exactly in tune. As the notes become closer in pitch, the frequency of the beat will decrease until they totally align and the beat disappears. This can be replicated by playing 440 Hz on the smartphone and slowly tuning up to that frequency on the tablet. In the next video, I'll show you some more visual demos to explain why instruments playing the same exact note will sound much different. Click that link on your screen to watch the video, and I'll see you there.